Just looking into the test for review sets, okay, and we have for part one, okay, just going back to one-to-one functions, and we're looking at determining the inverse as well as the domains and the ranges of both the one-to-one function and its inverse. And for what we have in the case of the first function, okay, so we have f of x set equal to 2x plus 3 over 5, and so for what we have in the setup, okay, so we got f of x is equal to 2x plus 3 over 5, okay, and setting the stage, okay, for finding out what the inverse is going to be. Okay, so again, for this f of x, okay, we have putting in terms of the variables x and y. So we have y is equal to 2x plus 3 over 5, and crossing over to what is going to be the inverse. Okay, so we initiate the process by interchanging the variables x and y. And so we have at the moment, okay, we got x is equal to 2y plus 3 all over 5, okay, and after the interchange we're looking at solving for y, and where that y is going to represent the inverse. Okay, so if I go ahead and get out of the fraction, so I can multiply both sides of the equation by 5. And so for what we will have at the moment, okay, is going to be 5x is equal to 2y plus 3. And solving for y, okay, so I'm going to isolate the y term, which we have with 2y, upon subtracting 3 on both sides. So now we're going to have 5x minus 3 is equal to 2y, and we have upon division by 2, so we have 5x minus 3 over 2 is equal to y, okay, and just switching sides by the commutative property of equality, again just going from the b is equal to a is equal to b mode. And for what we have in this y, again, is going to be the inverse. So we'll have the inverse of f of x is equal to 5x minus 3 over 2. And you can separate the terms, but you can leave as a consolidated rational expression. So you might have it as 5 halves of x minus 3 halves. If you're to put this in the slope-intercept format. Okay. All right. And so for what we have for this particular one-to-one function, okay, we don't have any restrictions like even root radicals or fractions. So we have for the domains and the ranges of the one-to-one function f of x and the inverse, where we have the inverse of f of x, we're going to have all real numbers throughout. Okay, so we have for the domain of f of x we have the set of all real numbers And the same thing we will have for the inverse. Again, for what we have in x in one will be for y in the other, and vice versa. Okay, and in terms of what we have between the one-to-one function and its inverse, again, in terms of graphing, okay, we're going to have symmetry with respect to the line y is equal to x. Okay, so for what we're going to have here, okay, again, a function and its inverse. Okay, if it's one-to-one, we'll have interchanging x and y coordinates. Okay, so you got like -14, -5 for y is equal to 2x plus 3 over 5, and we have -5, -14 for y is equal to 5x minus 3 over 2, and again, we have both of these graphs will have symmetry with respect to the line y is equal to x. And notice that all three of these functions will be intersecting at the ordered pair 1, 1. All right, and so we have again the domain and the range for both the one-to-one function and its inverse will be the set of all real numbers. Okay, now for what we have in the second function, now we got f of x is equal to the square root of 2x minus 4. Okay, and here we have a radical function that is an even root. And for this one, and we can go ahead and attain both the domain and the range. Okay. All right, so for f of x is equal to the square root of 2x minus 4. Again, 2x minus 4 cannot be negative, but it can be 0 or positive. So we have here, okay, we have 2x minus 4 can be greater than or equal to 0, and pinpointing, okay, what does allow for x to keep the even root radical function f of x is equal to the square root of 2x minus 4 defined. Okay, we're going to have 2x is greater than or equal to 4, and so we have in x, okay, we have for that containment, okay, we have the set of all values of x, okay, such that x is greater than or equal to 2. So we can go ahead and say that for the domain. Of f of x. Okay, so we have the set of all values of x. Whereupon we have x is greater than or equal to 2. And you can also use interval notation. So we have a bracket at 2. And we have going out to infinity, okay, which is boundless, thus the parenthesis. And now, for what we have in the case of f of x equal to the square root of 2x minus 4. Okay, in the case of tackling the range. Okay, so now y is equal to f of x is equal to the square root of 2x minus 4. And again, we have with the principal square root rule. Okay, so an even root radical term cannot reduce to a constant that is negative. So the square root of 2x minus 4, which defines y? Okay, it's going to be greater than or equal to 0. Okay, so that means we're going to have, for what is allowed in y, it's going to be where y is greater than or equal to 0. And so for this function, so for the range of f of x, so we're looking at the set of all values of y, whereupon y is greater than or equal to 0. And you can also put, even in the variable y, okay, you can use interval notation. In this case, we have a bracket around 0, and again, we have parenthesis around infinity. Okay, so now, even though we have not arrived at the inverse, we can go ahead and identify both the domain and the range of the inverse. So again, we have for the domain, the inverse, okay, what is going to be allowed in x. For the inverse will be what was allowed for y in the one-to-one function f of x. So in this case, we're going to have the set of all values of x such that x is greater than or equal to 0. And for what we have in the case of the range of the inverse, okay, so we're looking at the allowed values in y. So what is allowed in y for the inverse? We had allowed for x in f of x. So now we have the set of all values of y, whereupon y is greater than or equal to 2. So going from and including 2 on out to infinity. Okay. Now, and looking for the inverse of f of x is equal to the square root of 2x minus 4. Okay, so for f of x, putting in terms of y equals, so y is equal to the square root of 2x minus 4. And once again, interchanging the variables. Okay, so we'll come out to x is equal to the square root of 2y minus 4. And again, looking at squaring both sides. Okay, so for what we have on the left, okay, so we have x squared is equal to the square root of 2y minus 4, so that would be just 2y minus 4. And isolating the y term, so we have upon adding 4 to both ends, so we end up at x squared plus 4 is equal to 2y, and dividing by 2, we have that x squared plus 4 over 2 is equal to y. And you can split up the terms as well, or leave consolidated. So you're going to have for the inverse, in terms of the expression, so the inverse of f of x, so you have x squared plus 4 over 2, or 1/2 of x squared plus 2 if I were to split up. And this would be for the values of x, okay, that define the domain. So we're looking at those values of x greater than or equal to 0. So you have this included. So you have the x is greater than or equal to 0. So we're looking at the right half of the graph of this overall function for this to be 1 to 1. All right. And to also be the inverse of the given radical function we had for f of x equals the square root of 2x minus 4. And looking at what we have, once again we have with the graphs. Okay, so for y is equal to the square root of 2x minus 4, we have among the order pairs. Okay, so you have 2, 0, 4, 2, 10, 4, 26, and 34, 8. And switching the order, this will correspond to y is equal to 1/2 of x squared plus 2, or x squared plus 4 over 2 for values of x greater than or equal to 0. And so greater than or equal to 0. And just looking at what we have for these items. Okay, so we got, again, 0, 2, 2, 0, 2, 4, 4, 2 throughout. And so they share interchanges throughout. And again, both of these graphs will have symmetry with respect to the line y is equal to x. All right, now crossing over to what we have concerning properties of logarithms. And among them, okay, we've looked at the change of base formula. And now for what we have in looking at the values, so I'm just going to scroll down. Okay, and it says to evaluate each of the logarithmic expressions and equations. And it says here that if the result is not an integer or terminating decimal, then round to the nearest 3 places. Okay, so we have in this one, okay, so we have starting out with the base 5 logarithm of 26, and just looking at what we have here, so we're going to have that 26 is neither a multiple nor an integer power of 5. Again, just for the backdrop. Okay, so again, if you don't have a match where you can reduce the logarithmic term to a constant or whole number, okay, again, we have with our change of base formula. So you have the base A logarithm of m, we have equal to the base B logarithm of m all over the base b logarithm of a and the base b logarithm. Okay, if you're looking at the use of the calculator, we're looking at either natural or base 10 logarithms. Okay, so for what we have in the case of the base 5 logarithm of 26, okay, so m is represented by 26, a by 5. And if we look at reduction, and we'll just go with the natural log on this one. Same result will appear if you went with a ratio of base 10 logarithms. And so for what we have in the case of the natural log of 26 over the natural logarithm of 5, so this will come out to 2 point something. Yeah, so that's going to be about a 2.024. And for what we have in the case of the next item, okay, so we have for number 4, okay, so we have what's going to be the base 7 logarithm of a fraction. And this fraction we have with 19/13. Okay, and here we can say that m is represented by 19/13, a by 7. And this time we'll take the base 10 logarithms. So say we had the base 10 log of 19/13 over the base 10 logarithm of 7. And for the output here, to about the nearest 3 decimal places, we have 0.195. And for the next item, okay, so we had the base 3 logarithm of 38/3. Okay, so we have m at 38/3. A, once again, okay, we have in the lower position, okay, and this number we're going to have at 3. And again, you can apply base 10 or natural logarithms, and we'll just go with natural on this one. So we have the natural logarithm of 38/3 all over the natural logarithm of 3. And in this particular case, all right, to the nearest 3 decimal places, we're going to end up at 2.311. All right, now for number 6, okay, we're looking at to simplify matters. Okay, now we have not 1 but 3 base 54 logarithmic terms, and what we can do is that to find out, okay, the nearest value, okay, to the 3rd place, okay, what we can do is that we can combine these logarithms as a single base 54 logarithmic term. Okay, kind of going back to our sum and difference formulas. Okay, this time we're looking at, instead of expanding, we're looking at consolidating as a single base 54 logarithm. Okay, so for this we have the base 54 logarithm of 19 plus the base 54 logarithm of 25, and we have minus the base 54 logarithm of 10. Okay, and again, when we looked at our sum and difference formulas, okay, now we had implications between addition and multiplication, as well as what we had between subtraction and division. Okay, so doing a bit of gear shifting. If I look at consolidating as a single base 54 logarithmic term, okay, so you have a mix of adding and subtracting. Okay, so any attachments affiliated with positive logarithmic terms, they will go into the numerator. So you got 19 at the top. 25, okay, it's also going to be at the top. And since we have 10 as the attachment to a negative base 54 logarithm, okay, this will go on the bottom. And looking at what we have in following through, okay, so we had the base 54 logarithm, and we have 19 times 25 divided by 10. So we have a base 54 logarithm of 47.5, and if we utilize the change of base formula, okay, so m is at 47.5, a is going to be at 54, and we'll just convert this to base 54 logarithms. And so for what we have here, we have a base 54 logarithm, 47.5, divided by the base 10 logarithm of 54, and to the nearest 3 decimal places. Okay, so this will come out to 0.968. All right. And so we'll look into the sum and difference exercises. I'm going to tell you what I'm going to do here is that for what we have attached, we'll go ahead and take care of the change of base formula items for the study questions part in numbers 4 through 6. Okay, for there is another angle on this one. And say if we look at, for number 4 in this set, okay, so I had the base 3 logarithm of 24. Now 24 is a multiple of 3, but in terms of whole numbers, I cannot reduce this as such because while 24 is a multiple of 3, it is not an integer power of 3. So I can take what I have here. So you have m represented by 24, and 3 is going to represent a. I can just write what I have here as a ratio of natural logarithmic terms. So if I use the change of base through the natural logarithmic pathway, so I got ln of 24 divided by ln of 3, and so to the nearest 3 decimal places, okay, this will round up to 2.893. And for what we have in the case of the 5th problem, okay, so you have a base 5 logarithm of e squared, okay, and for this one, okay, you can use either natural or base 10 logarithms. We'll go with natural on this one. Okay, and for what we have in the mix, okay, so we have in the case of the display, so you got the natural logarithm of e squared all over the natural logarithm of 5, and so this will come out to 1.243 when rounded to the nearest 3 decimal places. Now I'll just go ahead and show you this. Okay, just looking at this through another angle. It would also work with base 10 logarithms, but I just want to mention something here. Okay, now by definition, okay, a natural logarithm is going to be a base e logarithm. And natural log of e squared have base e, logarithm of e to the second, and that would reduce to 2, and 2 over the natural logarithm of 5. It still comes out to the very same results, still at 1.243. All right. Now, for what we have in the case of number 6, now we got a base 6 logarithm of 216. Okay, and if you notice, okay, if you catch that 216 is both a multiple and an integer power of 6, you can write 216 in terms of base 6. So here we'll have the base 6 logarithm of 6 to the third power. And guess what? With the matching bases, exponential and logarithmic, okay, this will reduce to the raised power that we originally had. In this case, this is going to be at 3. And one might wonder, can you use the change of base formula if it doesn't quite jump out at you that the attachment happens to be a natural number power of the logarithmic base? And the answer to that question is yes. Okay, so if I were to go with, say, the base 10 logarithm or the natural logarithm of 216 over the same logarithmic base that we are using of 6, that will still come out to 3. Okay. Now, okay, so for these items, okay, we have the change of base. Now, kind of going back to what we have had with logarithmic expressions. Okay, so we have with the first part. Okay, now we have with numbers 7 through 9. Okay, these are a little bit tricky in a sense because we have radical expressions in the mix. And in terms of how to go about following through, so you have for the setup in number 7, I can go ahead and rewrite the radicals along the lines of non-integer exponents. So if I just go ahead and rewrite, so we have in the ratio. Okay, so you have x squared, and for the cubic root of y to the 5th, okay, that's going to be y to the 5/3. For the 6th root of z, okay, that's going to be z to the 1/6. And in the denominator, okay, so got 9. And the 4th root of b, okay, that is going to be b raised to the 1/4. And just taking what we have here, and again, just for the sums and differences of logarithms. Okay, so if I'm looking at expanding, again, multiplication will imply addition, division will imply subtraction. Okay, and if the attachments are at the top, we're going to have positive logarithmic terms. If the attachments are at the bottom, we're going to have negative logarithmic terms. Okay, so for the expansion, we're looking at into logarithmic base 3. So if I look at the top terms or factors, okay, so you have x squared. So we can start out, okay, with the base 3 logarithm of x squared, and with y to the 5/3 also in the numerator. You see we have plus the base 3 logarithm of y to the 5/3. And here we're going to have plus the base 3 logarithm of z to the 1/6. Now, with 9 and b to the 1/4 in the denominator, okay, once I write these factors out individually as attachments to base 3 logarithmic terms, okay, we're going to have subtraction. So you have minus the base 3 logarithm of 9. You have minus the base 3 logarithm b to the 1/4. Okay, and again we'll be looking at converting from exponents to coefficients. Okay, and just an adjustment to make. Okay, so 2 is going to be a coefficient. Same thing for 5/3, as well as 1/6. Okay, now for what I have in the case of the base 3 logarithm of 9, 9 is both a multiple and an integer power of 3. So I can rewrite this as the base 3 logarithm of 3 squared. Again, the 1/4 to which b is raised, okay, it's going to be a coefficient in the expansion. All right, so we have in the final layout, okay, we have among our terms, okay, we'll have what will be 2 times the base 3 logarithm of x plus 5/3 of the base 3 logarithm of y and we have plus 1/6 of the base 3 logarithm of z, and we have minus 2. And for what we have in b, we have minus 1/4 the base 3 logarithm of b. Okay. Now the terms don't have to be in that exact order, okay, but as long as you have these and the sign values correct, okay, this is when we have these 5 terms to result. All right. Now, for what we have in the case of also where we have a radical present, and we have for number 8, okay, so you have a base 5 logarithm, and we have a radical in the denominator. And if I rewrite this in non-integer power terms, so I have the base 5 logarithm of 7 x squared y cubed and you have all over w to the 4th. And for the square root of z squared plus 5, so that's going to be z squared plus 5 quantity to the 1/2 degree. And just looking at moving this and setting things up. Okay. All right, so we have in the ratio, so we have 3 factors in the numerator, 2 in the denominator. And now looking at expanding, so I can itemize what I have here. Okay, so first of all, I had the base 5 logarithm of 7. And we have plus the base 5 logarithm of x squared. And we have plus the base 5 logarithm of y cubed. Okay, so again, the attachments are in the numerator, so we're going to have positive base 5 logarithmic terms spun out. Okay, and for what we have in the denominator, okay, we'll create or have the creation of negative base 5 logs. So here we'll have minus the base 5 logarithm of w to the 4th. And we have minus, okay, the base 5 logarithm of the quantity of z squared plus 5 to the 1/2. Okay, and just looking at what we have here, so again, we're looking at writing powers as coefficients. Okay, now for the first term, we had the base 5 logarithm of 7, and to leave this in exact terms, well, 7 is neither a multiple nor an integer power of 5, so the base 5 logarithm of 7 is going to stay as it is. For the subsequent terms, okay, so we have 2 times, okay, the base 5 logarithm of x. We have plus 3 times the base 5 logarithm of y, minus 4 times, okay, the base 5 logarithm of w, and we have minus 1/2 of the base 5 logarithm of the quantity of z squared plus 5. Okay, and let me mention, okay, so this will be the final arrangement, and one might wonder, should something have been done to the 2 to which z was raised, okay, and put this in coefficient capacity? Well, what happens here is that for z squared in this expression, z squared does not stand alone, and because it is being added to a constant, if you have like plus something minus something, okay, because you're adding a constant, z squared is not standing alone, and so that 2 is not so maneuverable. If I had like just the base 5 logarithm of z squared and nothing added or subtracted from it, then the 2 would have been reconfigured. But with z squared plus 5, that is already baked in. Nothing further I can do with the square of z. So that is going to stay in the attachment. And so this will be your set of terms that we have in the case of number 8. Now, for what we have in number 9, okay, so you have a mixed bag of integer powers and also non-integers, and we have a radical that is in the mix. And if you notice in number 9 we have just log, and that is just the implicit notation for a base 10 logarithm. And you can specify what the logarithmic base is. Okay, so you have a base 10 logarithm, okay, and what I'll do here is I will convert this radical in terms of a non-integer exponent. Okay, so we've got 10, and I have u to the 3/4, and I have x to the 5th, and for the cubic root of z to the 4th minus 13, as a non-integer exponent. So I'm looking at z to the 4th minus 13, and the cubic root of this is going to be that expression to the 1/3 power. And we have all over w plus 1 to the 2nd. And you have times y to the 2/3. So just looking at what we have here. And there'll be somewhat a common thread between numbers 8 and 9. Okay, so for what we have looking at expanding, okay, and this time around, okay, so we have 4 factors in the numerator. And looking at itemizing, okay, so we have the base 10 logarithm of 10, okay, and with just 10, so we have implicitly, okay, that we have 10 to the 1st. Next we have plus the base 10 logarithm. And you can either write out the 10 in the subscript or just leave it as log. We have plus the base 10 logarithm. And we have x to the 5th. And we have plus the base 10 logarithm of z to the 4th minus 13. Raised to the 1/3 power. Again, looking at our powers and rewriting as coefficients. Okay, now first term had the base 10 logarithm of 10, or 10 to the first. Again, the bases will take care of each other. So first term goes to 1. And for the rest, again, we have 3/4 of the log, or base 10 logarithm of u, followed by 5 times, okay, the base 10 logarithm of x. And we have plus 1/3 of the base 10 logarithm of z to the 4th minus 13. Okay, so this is what I have at the top. Now for what I have at the bottom, okay, so again, anything that's at the top, we have positive logarithmic terms. Anything from the bottom, okay, I'm going to subtract. So minus the base 10 logarithm of the square of w plus 1, and we have minus the base 10 logarithm of y raised to the 2/3. Okay. And so in the completion of the set, okay, so we have minus 2 times the base 10 logarithm of w plus 1 minus 2/3 of the base 10 logarithm of y. Okay, and just like for the 4 for z to the 4th, okay, which is part of the binomial z to the 4th minus 13, again, because you're subtracting 13, z to the 4th is not itemized, and so I cannot transport the number as part of the coefficient, just like I could not move the 2 over, okay, because that z to the 4th, just like the z squared earlier, that's locked in. Okay, so we have, for this long statement, so we come out to, looks like 6 terms. Yeah, 6 terms in the mix, and we have just a constant 1 to lead off. Okay, now looking at expanding, and we say that for the second set. Okay, we'll go ahead and take on this, and for number 7 and 8. Okay, so if I go ahead and rewrite what I have in 7, just converting from radicals to non-integer exponents. So we had the base 3 logarithm of x squared. Now, for the square root of y plus 4, okay, so this will be y plus 4 quantity to the 1/2, and for the 4th root of the cube of z plus 2, okay, so you have z plus 2 quantity to the 3/4. And just setting the stage for expanding. Okay, so we have a set of base 3 logarithmic terms. Okay, so you have x squared at the top. So you have base 3 logarithm of x squared plus the base 3 logarithm of the quantity of y plus 4 to the 1/2. And then we'll have minus the base 3 logarithm of the quantity of z plus 2 to the 3/4. And once again, converting from exponent to coefficient. So this time around, okay, so we have 2 times the base 3 logarithm of x. And we have plus 1/2 of the base 3 logarithm of the quantity of y plus 4. And we have minus 3/4 of the base 3 logarithm of the quantity of z plus 2. All right. So we have 3 terms in the expansion. And just for the other one we have in terms of expanding, okay, so we got in 8. Okay, so we have the base 5 logarithm of 7t squared u to the third over v to the 5th times z. And I'll just go ahead and write this one out. So itemizing, okay, so you have the base 5 logarithm of 7. And you have plus the base 5 logarithm of t squared plus the base 5 logarithm of u to the third, and with v to the 5th and z in the denominator, we have minus 5 times the base 5 logarithm of v to the 5th minus the base 5 logarithm of z. Okay. And so for what we will have, okay, in the end result, okay, so again we have 7 relative to 5. 7 is not a multiple or an integer power of 5. So again we have the base 5 logarithm of 7, and for the remaining terms we have 2 times the base 5 logarithm of t plus 3 times the base 5 logarithm of u, and we have minus 5 times the base 5 logarithm of v, and again we're going to have minus the base 5 logarithm of z. All right. Now, in the crossover, okay, so what we have looking at consolidating logarithmic terms. Okay, now we have in the case of number 10, okay, so you have 2 times the base 5 logarithm of 10 plus 3 times the base 5 logarithm of x, and we have minus 2 times, okay, the base 5 logarithm of y. And for the setup we have in number 10, and what we can do here, okay, is that notice we have for the coefficients, we can make those into exponents because we're going, instead of expanding, we're looking at contracting. So for what we had in the initial process, okay, so we have the base 5 logarithm of 10 squared, and we have plus the base 5 logarithm of x cubed, and we have minus the base 5 logarithm of y squared. Okay. And after putting the items along the lines of just adding and subtracting, where we have the coefficients converted to exponents, so we have the base 5 logarithm, and since we have addition and subtraction, we're going to have a fraction. Okay, so we got the base 5 logarithm. So you have 10 squared, and we have plus. Okay, so the addition signals that x cubed will be at the top. Subtraction of the base 5 logarithm of y squared. So that's going to be with y squared on the bottom. And 10 squared, okay, I can just specify that numerical value. Now, if you had a written exam and you left it as 10 squared, I would count that as correct. And 10 squared is 100, so we have 100 x cubed all over y squared. Okay. Now, for what we have in the case of 11, okay, so we're looking at writing as a single logarithm. Again, we have exponents that we can originate from the coefficients. So we have, in the case of 11, okay, so we have the natural logarithm of u squared plus the natural logarithm of v to the third plus the natural logarithm of the quantity of u plus v to the 1/2 minus the natural logarithm of w to the 4th plus y to the 5th minus z to the 3/4 degree. And so putting what we have all together, so you got the natural logarithm. Okay. Positive terms have the attachments in the numerator. So you have u squared, v to the 3rd, and u plus v quantity to the 1/2 also in the numerator. And with the last term being a negative, okay, the attachment will go in the denominator. Okay, so this is one way that you can express your final answer, and another one would be, and I have seen some put the non-integer exponents as radicals. So you could also have this as the natural log of u squared v to the 3rd, and for u plus v all raised to the 1/2, we say we have the square root of u plus v. And for what we have in the denominator, okay, so 3/4 degree signals that the index number of the radical will come from the denominator, which we have at 4. So you have the 4th root of this sum of terms raised to the 3rd power. Okay. All right. Now, for what we have in the case of item number 12, what I'm going to do here, see if I can duplicate this. You have a bit of dual situation here, because you got, for the attachments, you have radical terms, but you also have coefficients at the front, and these are going to mingle together to where we can still consolidate all we have in this problem as a single logarithm. So in the case of number 12, okay, so we've got radicals in the attachment, and what we can do is go ahead and write, okay, what we have in the cubic roots along the lines of non-integer powers. Okay, so we got 12 times, okay, the base 5 logarithm for the cubic root of y minus 4. Okay, that'll be the quantity of y minus 4 to the 1/3 and we have plus 2 times. I could go ahead and write the 2 as a power, but I'm just going to save that for the next step. So yeah, plus the base 2 times the base 5 logarithm of the quantity of y squared plus 15, and I have minus 5. Again, just rewriting the radical. So minus 5 times the base 5 logarithm of the quantity of y plus 5 raised to the 1/3. Okay, so got the coefficients, which I'm going to put in exponential position. And for what we're going to have in the follow-through, especially for the first and the last terms, okay, there's going to be a power property of exponents follow-through in addition to what we have been accustomed to at this stage. Okay, so we've got the base 5 logarithm. Now we have y minus 4 to the 1/3. And we have taken to the 12th. We have plus the base 5 logarithm of y squared plus 15 quantity squared. And we have minus the base 5 logarithm and we have quantifying, so we have the quantity of y plus 5. We have raised to the 1/3, and again you're going to have raised to the 5th power. Okay, so we have in the case of the power property, okay, so you had the base 5 logarithm. And for y minus 4 to the 1/3, taken to the 12th, okay, so you're looking at y minus 4 raised to the 1/3 times 12 degree. And so 1/3 times 12 is going to be 12/3, and that's going to go to 4. So you have the base 5 logarithm of y minus 4 raised to the 4th. We have plus the base 5 logarithm of the square of y squared plus 15. Again, we have minus the base 5 logarithm. And for y plus 5 to the 1/3 and then raised to the 5th, okay, again, multiplying the powers. So we're going from one non-integer exponent to another. So in this case, we're going to have now y plus 5 raised to the 5/3. And now now that we have taken care of the coefficients, we can go ahead and consolidate as a single base 5 logarithmic term. So we have first term in the trio, okay, we have a positive, so we have y minus 4 to the 4th at the top. And the next term in the previous step is positive, so y squared plus 15 raised to the 2nd is also going to be in the numerator. And with the subtraction of the last term, we're going to have the quantity of y plus 5 to the 5/3 in the denominator. Okay. And again, just another way. So yeah, base 5 logarithm, so you have y minus 4 to the 4th. times the square of y squared plus 15 and you can display what we have in the denominator as a radical expression. So we got 5/3, and the 3 in the denominator indicates the nature of the radical, which would be a cubic root, and it's going to be that of the 5th order of y plus 5. Right. And also we have looking at consolidating logarithmic terms, okay, and we have with the subsequent group, and we have for this set for 9 and 10. Okay, so we have this one. Okay, so again we just make the coefficients into exponents. So now we're going to have the base 5 logarithm of w to the 3rd minus the base 5 logarithm of x squared plus the base 5 logarithm of y minus 4 to the 6th, and we have minus the base 5 logarithm of z to the 3rd. Okay. And so, looking at what we have in consolidating. Okay, so you don't have any leading coefficients other than 1. So we can go ahead and kind of separate the attachments. So we'll go in the numerator as well as the denominator. Okay, so we have for w cubed, this comes from a positive base 5 logarithmic term. So in the consolidating, w to the 3rd will be at the top. X squared comes from a negative, so that will be put in the bottom. Then we have y minus 4 to the 6th. This comes from a positive, so that will be in the numerator. And with z cubed, this comes from a negative base 5 logarithmic term, and in the consolidating, okay, z cubed will go on the bottom. And for what we have in the case of number 10, okay, so we have here, okay, so we've got a radical that is in the mix. So looking at what we have now, okay, so rewriting what we have in the square root. Okay, so the first term, okay, so we have 2 times, okay, the base 3 logarithm of u plus 3 times the base 3 logarithm of the quantity of v minus 4. Then we have minus 3 times the base 3 logarithm. Okay, and for the square root of w to the 4th minus x cubed, you see I have w to the 4th minus x cubed to the 1/2 power. Okay, so, and moving the coefficients, so we have in the rewrite, so we're going to have the base 3 logarithm of u to the 2nd, and I have plus the base 3 logarithm of the quantity of v minus 4 raised to the third, and we have minus the base 3 logarithm. So we have the quantity of the quantified expression w to the fourth minus x cubed, which would be to the 1/2, and then furthermore raised to the third. Okay, so we have the base 3 logarithm of u squared plus the base 3 of logarithm. Okay, we have of the quantity v to the minus 4 raised to the third. We have minus the base 3 logarithm, okay, and then putting together. So I have the quantity of w to the fourth minus x cubed, and to the 1/2 and to the third, so this will be to the 1/2 times 3, so this will be to the 3/2 power. And now I can put all together as a single term. So we have a base 3 logarithm. Okay, so we have u squared, and I have times the quantity of v minus 4 raised to the third, and we have with the last term being subtracted, so that attachment goes in the denominator. And again, in the display, the non-integer exponent portion can be displayed as a radical. Okay, so the alternate final answer we can have as u squared times the cube of v minus 4, and with 3/2, so we have the square root of w to the fourth minus x cubed to the third. All right, and okay, so these are what we have in the case of consolidating logarithmic terms. Now, for what we have now in the crossover, and we have with exponential equations, and again, if we look at those items, okay, say that we'll have common exponential bases. And from the first set, it looks like the only one we have is going to be with number 13. And for this one, okay, so we got 8 to the x plus 6. Is equal to 4 to the x. Okay, so for 8 to the x plus 6 equal to 4 to the x. Okay, now for what we have in the equation, okay, so 8 is a multiple of 4, but it is not an integer power 4, so we can sort of take a step back, and we have a number that will multiply into both 4 and 8, and that is going to be with the number 2. So if I convert what I have with 8 and 4 along the lines of base 2, okay, so for 8 is going to be 2 cubed, and for 8 raised to the x plus 6 power, we have 2 cubed to the x plus 6, and for 4 to the x, 4 is 2 squared, thus 4 to the x will be 2 squared raised to the x. And for what we have in the follow through, okay, so we have on the left, so we have 2 raised to the 3 times all of x plus 6, and that's going to be equal to 2 raised to the 2 times x power. And looking at distributing, so we have 2 raised to what is going to be, so for 3 over the quantity of x plus 6, that is going to be 3x plus 18. Okay, so I got 2 to the 3x plus 18 is equal to 2 to the 2x. Now I have single base 2 terms, and I can go ahead and set the powers equal to each other. Okay, so I have 3x plus 18 is equal to 2x. So we have 2x by itself, and so I can just move the 3x over to the other side. So we're going to have the 18 is equal to negative x, and if I just change the signs at both ends, it's got negative 18 is equal to x. So the missing value x that will make this equation ring true will be negative 18. Okay. And for what we have in terms of the second set, okay, so here we got with the first item, so you have 8 to the x plus 2 is equal to 4 raised to the 2x. Okay, and it's going to be a bit of history to repeat, okay, for we're going to have, in this situation, okay, we're going to have a common base, once again with 2. Okay, so for 8 to the x plus 2, if I put in terms of base 2, so 8 is 2 cubed. We have to the x plus 2, 4, again we have 2 squared. And that is going to be to the 2x. Okay, and again, with the power property of exponents. So for 2 cubed to the x plus 2, so you have 2 raised to the 3 times all of x plus 2, and that's going to be equal to 2 raised to the 2 times all of 2x. And we have 2 raised to the 3x plus 6 power, and that's going to be equal to 2 raised to the 4x. Okay, so nothing extra like in terms of inverse rule or the power or the product property of exponents, for I now have single base 2 terms, and so the light is green to go ahead and place the powers and set equal to each other. So here we got 4x plus 6 is equal to, make that 3x plus 6 is equal to 4x. Okay, so I have 4x by itself. And if I join with 3x upon subtracting 3x from both sides, and we have in the end result, okay, we're going to have that the value of x will end up as 6. And that would be the final result for this particular problem. Okay, and now, so another case of what we have for equations, exponential equations that share a common base. Now, okay, now in the case of what we have regarding exponential equations with no common base, and again, just as useful tools, if you happen to have the variable to be on one side of the equation. Again, you can reference our earlier logarithmic properties. Okay, and so just kind of starting out with where we have the variable on one side of the equation. So if we're looking at solving for x, and we'll say that we have like 9 to the x plus 4 is equal to, we'll say, 1,000, or we'll say 10,000. So you have 9 to the x plus 4 is equal to 10,000. And as long as you have the variable on one side, okay, so we have our 9 to the x plus 4 equal to 10,000. Okay, if you had the variable on one side of the equation, you could use the first logarithmic property. So you could just convert, okay, that where we can eliminate the exponential base, so we can take base 9 logarithms on both sides. Okay, so for the base 9 logarithm of 9 to the x plus 4, okay, so this will go to x plus 4 and here we have x plus 4 is equal to the base 9 logarithm of 10,000. Okay, and what I can do here is that for the base 9 logarithm of 10,000, I can either use natural or base 10 logarithms, where a is represented by 9, m is represented by 10,000. Let's say we'll just go with log. And so for what we've got in terms of base 10 logarithms, they have the base 10 logarithm of 1,000 divided by the base 10 logarithm of 9. Okay, so for this ratio, so this would be like 4.1918. And in solving for x, if I take this result and subtract 4, say round to about the nearest 4 decimal places, so we have about 4.1918. Okay. Now let's say that if we have so we have 5 to the x plus 2 is equal to, and we'll say that we have is equal to 333. Okay, so you got the variable on one side. So I can take care of the exponential base 5 by taking the base 5 logarithm on both sides. Okay, so left-hand side. Okay, so we're going to have an x plus 2 have is equal to the base 5 logarithm of 333. And for what we have here, so I can apply the change of base formula. Okay, and I'll just go with the ratio of natural logarithms. It'll still work for base 10. So for what we have here, so we got x plus 2. And for the ratio of the natural logarithmic terms, so we got the natural logarithm of 333 over the natural logarithm of 5. And we have among the first digits, okay, so you have 3.60880. And if I take 2 away, okay, so for the approximate value of x, so if we take to about the nearest 4 decimal places, so we have x to end up right at 1.6088. Right. So these are cases where we can utilize, okay, our first logarithmic fundamental along with the change of base formula. And this is whenever you had the variable that we're solving for in an exponential equation to be on one side of the equation. Now, here's a rule of thumb. Okay, if x happens to appear on both sides, you're going to apply, okay, ln or log on both sides. Okay. And just kind of give you a bit of a backdrop. Okay, so if you had the variable to appear on both sides, and without changing things up too much, let's say if I had 9 to the x plus 4 is equal to 10,000. I'll say we have 10,000 that's raised to the 2x minus 1. Okay, so we got for 9 to the x plus 4 is equal to 10,000 to the 2x minus 1. You can apply either ln or log to both ends. Doesn't matter which one you apply. You might be tempted to go with log since we have 10,000, which is a power of 10, but I tell you what, we'll go with natural log in this one. Okay, so we have natural logarithm of 9, okay, raised to the x plus 4 is equal to the natural logarithm of 10,000 raised to the x minus 1. Okay, and in this particular setting, now in terms of following through, okay, you're going to be entering the scene, okay, another property, one of the earlier ones. If you have like, don't have a match between the logarithmic and exponential base, say if you have like the base A logarithm of m to the r, again, the exponents you can rewrite as coefficients. You have r times the base A logarithm of m. So what I mean by this is that for what I have in this step, okay, so I have x plus 4, I'm going to put this at the front, likewise for 2x minus 1. And to indicate that all of x plus 4 is going to multiply the natural logarithm of 9. So we have the quantity of x plus 4 times the natural logarithm of 9 is going to be equal to all of 2x minus 1 times the natural logarithm of 10,000. Okay, so we still have a couple of x terms on both sides. And what we're going to do next, okay, so I'm going to distribute like x and 4, or like negative, I should say natural log of 9 over x plus 4. So I can say that I have, removing the parentheses, okay, so I have x times the natural logarithm of 9 plus 4 times the natural logarithm of 9 on the left, and with the distribution on the right, I can say that I have 2x times the natural logarithm of 10,000 minus the natural logarithm of 10,000 Okay, so we have variable terms apart from each other. And what I'll do here is that, okay, so I got x terms on both the left and the right. And what I can do here, I'm going to join our x terms. And what I'll do here is just, I'm just going to go ahead and have the x terms on the left. And just have the non-variable logarithmic terms on the right. So I'm just going to move 4 times the natural logarithm of 9. Okay. And so looking at putting together, you have x times the natural logarithm of 9 minus 2x times the natural logarithm of 10,000 is equal to the negative of the natural logarithm of 10,000 minus 4 times, okay, the natural logarithm of 9. Okay, and so I got x terms both on the left hand side, and to still solve for x, what I can do is that I can factor out what I have in x. So if I factor out x, so I have x times the natural log of 9, and factoring out x in the second term, so we have x times negative 2 times the natural logarithm of 10,000 Okay. And now looking at itemizing x. So I'm going to divide the right hand side by this difference on the left. Okay, and just kind of put this in the calculator notation. Okay, what you're going to do, I'm going to do a little bit of color coding. Okay, so if I were to put this as like a contiguous statement, okay, so I have, starting out with parentheses, so I can say that I have open parenthesis, the negative of the natural logarithm of 10,000 minus 4 times, okay, the natural logarithm of 9. So I'm going to close out for 9, and I'm going to close out for the statement. So this is what we have in the numerator, okay, and then we have for the denominator. Okay, so I'm dividing by all of this difference. So you have the natural logarithm of 9 and we have minus 2 times the natural logarithm of 10,000 okay, so I'm closing out, okay, for 10,000, and then with the blue, okay, this is indicating that I'm closing out for the denominator, okay. So in terms of the numerical value of x, say if I were to round to about the nearest 4 places, okay, so we got the negative of the natural logarithm of 10,000 minus 4 times the natural logarithm of 9, close out for 9, close out for the numerator, then I have divided by the quantity, so I got the natural logarithm of 9 minus 2 times the natural logarithm of 10,000 and for this particular result, so you have for x, okay, that's going to be about a 1.1095 whenever rounded to the nearest 4 places. Okay, so x is about 1.1095, and you can do kind of a quick check. Okay, so just looking at what we have here. Okay, so you have for 9 raised. Okay. So you have 75,110 point something. And for 10,000 raised, okay, to the 2 raised to the 2 times 1.1095 minus 1, and there's going to be some level of discrepancy. So you got like 75,110 point something on the left, and to the right you have 75,162 on the right. And the reason for this difference, okay, is because of rounding off, okay, to the 4th decimal place. If I had taken it out to like the 7th or 8th, these numbers would be more of a 1-to-1 match. But so we have to the nearest 4 places, you have about 1.1095. Okay, and okay, we're kind of heading home to the final stretch, and there are a few more things we'll be looking into, and I would say probably the most intense part by far is where you have the exponential equations that do not share a common base, and there are other items we'll look into, and this will be just the remainder with the business applications, as well as what we're going to have in the case of logarithmic equations, which will be in very close relation to what we have with exponential equations. And I'm going to let this be our stopping point. If anybody has questions, I will stick around. Otherwise, we'll pick up next time on Tuesday.